Hi, I'm Vince. I direct the Foundations of Cooperative AI Lab at CMU together with Casper, who will speak next. And I wanted to talk a little bit about, I'm interested in many of the ideas here, but I'll focus specifically on one, which is cooperative AI through simulations. And the thinking being that when interacting with an AI agent, one thing that you could do is to just run that agent in simulation, potentially, right? That's something that's not really a familiar human idea. I mean, I could try to form a model of somebody, right? I could have maybe some model of Kate, since Kate and I go back quite a way. But it's not perfect. I can't truly simulate her. But with AI models, you really could do this. So that's what I'll talk about. I'll talk about this position paper that I just put on the web. This is with Vojta, Eric, Sami, and Alexis. I know we were talking about the asterisks before. I just noticed yesterday there's an asterisk next to my name. I'm an imperfect recall agent. I can't remember whether I agreed to this or not, but I'm the corresponding author. That certainly does not reflect the amount of work put in, which was certainly Vojta's. Maybe it reflects that I didn't do enough, and it's a punishment. But good. Anyway, you can also find the paper with this QR code here. I like this model in part because in our lab we kind of struggle with, well, we want the techniques that we develop to be actually relevant to real systems on the one hand. On the other hand, systems change, right? And tomorrow's AI may not look like today's AI. I think it's very good that we've already seen a number of talks here by Jijin and Mike and Aaron, where we're evaluating language models and whether they cooperate in various contexts. I think that's good and important work to do. And we have a nice collaboration already going on with Jijin. But from that, we also see that things change, right? You add the reasoning component, and now suddenly they're a lot less cooperative. And who knows? Maybe the training data changes, the prompt changes. How do you know that something is robust? So we'd like to make not too many assumptions. You can go into theory, but then, of course, if you make the wrong assumptions, it's also not very relevant. I feel like this is a pretty minimal assumption that typically, if we have some AI system, if nothing else, we should be able to run it, right? Even with today's language models, in spite of all the mechanistic interpretability work, I think still the way we learn about these systems is just by running them, right? Playing around with them, maybe via the API, direct, whichever way you want, but that's how we learn about these systems. So we can think about this as AI agents running each other in simulation. You can also think of it as kind of a model for testing AI before we release it, before we deploy it, right? So think about, or maybe auditing, red teaming, all these kinds of things, where we're somehow evaluating the model just by running it in various ways. So let me talk a little bit about what is in this new position paper, and then I'll talk about some of the older work also with Casper. And one of the points that we make in this paper is that we should also think about strategic behavior. More generally, should you feel comfortable about deploying an AI system based on tests that you did on it, right? Having done a number of evaluations, should you be comfortable? And we already know from practice that many ML systems, once you deploy them in practice, they don't actually work as well as you thought they would based from your testing data. That can be due to a number of different things. It could be due to drift. My favorite example was still, I remember many years ago, there was a researcher who was doing economic sentiment analysis on then Twitter. And the model had picked up the fact that the word benefits, that was a useful word. That if people were tweeting benefits, that was a useful signal about the state of the economy. Until the movie Friends with Benefits came out, and it was completely, the signal was ruined. Okay, many of these types of things, the model is trained on data from one hospital, deployed in another one, doesn't work as well. It could be due to strategic behavior on the part of the users, different kind of strategic behavior. For example, if you use AI to screen resumes to decide who to interview, you can be sure that people are going to change how they write their resume based on that software. And we all know about adversarial examples, and your system might interact with another system as well. But here I want to focus a little bit more on the system in some sense wanting to behave differently. It's a loaded word. I was just at a conference on intentions in AI with many philosophers and neuroscientists. So I don't mean to put too much meaning into this word, but if you want to just say it behaves as if it wants to behave differently. which could be due to different reasons. It could be coded in by the developer, right? The developer is actually trying to sneak one by us and have the AI do something that maybe we don't want it to do. We'll see a sort of example of that next. It could also be not so much, truly agentic as more due to selective training, right? That we only, we do the fine tuning in a very particular way. We have very particular examples, but it actually doesn't generalize quite as well as we like. Or it might somehow be emergent. So especially for those kinds of things, we argue for a game theoretic approach. And I want to give you a little bit of a sample of what that might look like. That game theory may be a good tool for thinking about this. Here, by the way, is that example of coded in by the developer. You may remember the scandal of the Volkswagen emissions scandal, where the car would actually detect whether it was being emissions tested. And if it detected that it was being emissions tested, it would go into full eco mode and not pollute very much. And conversely, if it detected that it was just on the highway with an actual driver, then it said, forget about the eco mode, we're just going for performance. That one got caught. But it's a good illustration of the fact that, of course, you don't want the system or the AI to know that it is in simulation. Let's see if we can see this formally. So one of the things that it would be particularly useful for is trust, right? If I don't trust the system, then running it in simulation might let me trust the system. And so let's go to the trust game. We just heard about the donor game from Aaron. Trust game is similar, but it's one round, two-stage game. Here's the game tree. You might notice it's sort of slanted to the left. That's because I'm going to add something to it, simulation. But the basic version of the game is like this. Player one starts with some amount of money, let's say 10. Okay. This one is actually run on human subjects quite often. So that's how we're going to present it as well. Player one has 10. And now player one can choose, actually, player one starts with 5. Player one can choose to give that 5 to player 2. Okay? And now the thing is that if player one gives to player 2, that money gets tripled first before player 2 receives it. Sometimes it's called the investment game. Maybe player 2 has this brilliant startup idea that's clearly going to triple the value. If player 2 receives the money, player 2 has 15 and now gets to choose whether either to run off with all that money and player 1 is left with nothing, or to give 10 of it back to player 1. Okay? Now, the straightforward analysis game theoretically of this game is to say, well, clearly player 2 has every incentive to just run off with the money. Player 1 can perfectly well anticipate that and so isn't going to give the money in the first place. So we end up here, 5, 0, which is frustrating because we could have ended up over here where everybody would have been happier. And this, of course, is a familiar lesson from game theory that pursuing our own incentives might lead to an outcome that is worse for everybody. There's an interesting ethics angle to this that I also appreciate, so, but that's a bit of an aside for now. Here we're going to think about adding a simulation step. So now player 1 can suddenly also try to, or choose to simulate player 2. And then we get the following game, where if player 1 chooses to simulate, that costs player 1 1. Then simulated player 2 will have to make a decision. Do I give money back or not? So this is giving money back to the left. This is not giving money back. To keep it all fitting on one slide, I'm just going to assume here that if player 2 in simulation doesn't give the money back, then player 1 in real life is not going to give money to player 2. Okay, so then the game ends here. Player 1 says, well, that was too bad, but I'm at least going to keep the remaining 4 that I have. Whereas if player 2 actually in simulation decides to cooperate, then player, again, I'm sort of skipping a node here to keep it on the slide. I'm going to assume that player 1 in that case will give the full 5. And now the real world player 2 has a decision whether to give back the 10, right, leaving player 1 with 9 because spent 1 on the simulation, or again, run off with all the money. Okay, how should this game be played? Well, it's very simple. If you're player 2, if you're being simulated, you behave nice, and if you're in the real world, you run off with the money. Okay, well, that's not the intent. And so really we have to make sure that it's indistinguishable to player 2 whether it is in simulation or not. Okay, and this is in game theory what we represent with these information sets. Player 2 cannot tell the difference between the nodes that are connected with these dotted lines. Okay. This is a particularly interesting type of imperfect information, namely it's imperfect recall. Right? As I had at the beginning of this talk, that here in some sense the way this looks is like player 2 has played here before, has played in simulation before, but of course cannot recall what player 2 did in simulation, right? Because it's two different copies. But we can naturally model this as imperfect recall. This leads to lots of interesting problems in game theory, going into philosophy as well, because you have to think about how likely is it that you're currently in a simulation as an AI system. Where do you expect yourself to be? So it actually is somewhat non-trivial what ends up happening, and there are variants of the model where you learn about the agent's mixed strategy versus the actual action that the agent takes, and those give somewhat different results. There's also quite a bit of work on, if you know program equilibrium, this involves the agents being transparent to each other, and so you can also think about the agents simulating each other. Casper has some very early work on this. And you might think this is tricky because if we're both going to simulate each other, well, once I simulate you, I have to simulate you simulating me, which involves then again, okay, this doesn't end. But Casper figured out that, well, that's actually not so bad because we can put some small probability on not simulating, and then this thing will end. This gets very tricky once you get the 3 or more players, because then if I'm simulating 2 other players, and each of those are simulating the other 2, then actually this all blows up exponentially. We have a nice recent paper led by Emery that actually in some sense addresses this well, but you have to be, it gets technically quite hairy, but the solution I think is nice, that actually ensures that this whole thing halts and still gets you the benefits that you want. Okay, with that I think I'm out of time, but happy to talk more with anybody who's interested.